Astronomers have discovered the biggest galaxy known to date, and it's so big, it will break your brain. It's a radio galaxy, lying 3 billion light-years away from us, in the constellation of Lynx. This means that light from this galaxy, traveling at 300,000 kilometers per second, takes 3 billion years to reach us. This mammoth galaxy has been named Alcyones, and it has puzzled astronomers. But what is a radio galaxy? How is it different from the galaxy we live in? And most importantly, how big is it compared to the Milky Way? Our journey of exploring galaxies has been an interesting one. About a century ago, we believed there was just one galaxy in the entire universe, the Milky Way. Of course, we had pictures of other galaxies, like the Andromeda Galaxy, but astronomers believe them to be stellar systems of the Milky Way itself. 100 years later, the number has gone up to 2 trillion. Astronomers have seen a variety of galaxies in the universe. They include spirals, ellipticals, irregulars, lenticulars, lopsided, interacting, and merging galaxies. But this is an apparent classification based on what we see through a telescope in the visible region of the electromagnetic spectrum. Objects in our universe radiate energy over a wide range of frequencies, and depending on this energy emitted by them, they show varying luminosities in different sections of the electromagnetic spectrum. This means that there might be an extremely dull object in the visible spectrum, but can appear very bright when seen in radio or infrared light. So the galaxies that are very luminous at radio wavelengths are known as radio galaxies, and Alcyones is one of them. Now the question is, what makes radio galaxies unique? What extra information do we get when exploring the sky and radio frequencies? Radio emissions are one of the best ways to decode the mysteries of our universe. As radio waves have longer wavelengths, they can also travel through dense dust clouds, thereby providing unobstructed views of the cosmos otherwise not visible in the optical spectrum. There are different emission mechanisms via which astrophysical objects emit radio waves. However, the most common emission mechanism is the synchrotron emission phenomenon, and most radio galaxies majorly emit radio frequencies due to this phenomenon. Now what's that? You must have heard of cyclotron radiation in your high school physics classes. When electrons moving in a circular orbit in a cyclotron get accelerated in the presence of a magnetic field, they emit radiation corresponding to their cyclotron frequency. Now, synchrotron radiation is just a relativistic twin of cyclotron radiation, as electrons, in this case, are traveling at relativistic velocities. Hence, synchrotron emission is one of the most powerful and dominant mechanisms of radio emissions. Like other galaxies, radio galaxies consist of a host galaxy, comprising stars orbiting a galactic nucleus containing a supermassive black hole. This is accompanied by colossal jets and lobes erupting from the galactic center. These jets and lobes interact with the intergalactic medium and eventually act as a synchrotron to accelerate electrons that produce radio emission. This process is quite common, and even the Milky Way has radio lobes. But in some galaxies, the radio lobes mysteriously grow up to megaparsec scales. And this is why such galaxies are known explicitly as radio galaxies. While hunting for the largest radio galaxy, the team looked into the data collected by the Low Frequency Array, better known as LOFAR. It is an interferometric network consisting of about 20,000 radio antennas distributed throughout 52 locations across Europe. LOFAR aims to map the universe at radio frequencies from 10 to 240 megahertz with greater resolution and greater sensitivity than previous surveys. And at present, LOFAR is the most sensitive low-frequency radio telescope active today. So the data from LOFAR was reprocessed, and all the possible compact radio sources that might have interfered with detections of diffuse radio lobes were removed. Then the team manually surfed through the remaining candidates, and Alcyonus was found, spewing forth from a galaxy a few billion light-years away. The galaxy spans 16.3 million light-years in space. Some 100 Milky Way galaxies laid end to end would about equal the length of this newly discovered galaxy. After measuring the giant lobes, the researchers used the Sloan Digital Sky Survey to understand the host galaxy in detail. Eventually it was found that Alcyonus is a normal elliptical galaxy embedded in a filament of the cosmic web, clocking in at about 240 billion times the mass of the Sun. Moreover, it is graced with a supermassive black hole at its center, having a mass almost 400 million times the Sun. Since both these parameters lie at the low end for giant radio galaxies, this can provide some clues as to what drives the growth of the mammoth radio lobes. Moreover, Alcyonus and its hosts are suspiciously ordinary. The total low-frequency luminosity density, stellar mass, and supermassive black hole mass are all lower than what is expected for giant radio galaxies of this scale. This suggests that massive galaxies or central black holes are not prerequisites to growing large radio giants. In addition, Alcyonus is sitting in a region of space with a lower density than average. Probably, this could have enabled its expansion, and it is believed that Alcyonus is growing even bigger, far away in the cosmic dark. Although millions of radio galaxies exist in the observable universe, only less than 1,000 giants have been found to date. Due to this, the list of mysteries associated with Alcyonus and other radio giants is still quite long. Still, with more sensitive radio telescopes, like Square Kilometre Array, coming on board in the future, we can expect to have some exciting revelations in the coming years.